This is section 14.5, signal characteristics in regards to shape. So what is meant by that is that sometimes whenever you collect the IR spectra of a molecule, you'll notice that there are there are large differences in shape of each stretch. For instance, some will be very broad, taking up a large amount of the frequency spectra, whereas some will be sharp. And the reason why this happens is due to a lot of things, but mostly hydrogen bonding. So a hydrogen bond can weaken, it can weaken a signal, or it can change the symmetry of a signal. This is a little more advanced in organic chemistry, but infrared spectroscopy has a lot to do with the symmetry of a molecule. And as you have differing hydrogen bonds, such as this one or this one, you are changing the types of vibrational modes that can happen in a molecule and the strength of those modes, and you're changing the types of vibrations that can happen, like with this hydrogen bond, for instance. So because of all of the different types of interactions that this represents, you see, instead of one sharp signal, you see a broadening of the signal over the spectra, meaning that there are several related molecules that are giving rise to this signal, and it's very difficult to pick just one apart. What's interesting is if you take a molecule that has hydrogen bonding and you take it away from the hydrogen bonding environment, you can turn a broad signal into a sharp one, because instead of having many hydrogens around, you only have the one that you're looking at. This is a really big issue in carboxylic acids, just like it is for alcohols. In carboxylic acids, you have a very strong tendency to do what's called a self-hydrogen bonding interaction, or a dimerization. And because you can have this type of dimerization event, you can have a very broad OH signals in the IR spectra. One kind of funny IR spectra that you might run across are those of amines. And amines have a broadening not due to hydrogen bonding per se, but due to asymmetry. So for instance, if you have these two amines, perhaps propylamine and dimethylamine, the two spectra will look very different. In the propylamine, you'll have two peaks, one slightly broader than the other, but in the dimethylamine, this one, you'll have one broadened peak. And why might that be? It might be easy to say, oh, well, the NH2 has two hydrogens, so two signals, right? Not exactly, because the amine has two types of stretches it can do. It can either do an asymmetric stretch, where the one hydrogen comes toward the nitrogen and the other hydrogen goes away, or it can have a symmetric stretch, where both hydrogens are going away from the nitrogen. Because of these two stretches, you have two signals in the IR spectrum. This is in stark contrast to dimethylamine, where you only really have the symmetric stretch of the hydrogen in regards to the nitrogen. And that's why you have only one signal in dimethylamine instead of the two signals in the NH2 group. So be careful when thinking about the assignments of functional groups and how many signals you think they should have. It's not tied to the number of hydrogens that might broaden a signal. It's tied to the types of stretching modes that can happen in those molecules. And this has been section 14.5.